introducing myself. My name is Marlyn Li, and as Elizabeth mentioned, my topic is the acoustic ray propagation in an ellipsoid. So the guiding question for my research was, how can we optimize sound recording for a concert hall setting? Currently, the most common method of recording is close miking, and this involves placing the microphone directly on or very close to the instrument. This has issues in the fact that instruments are largely made to be enjoyed from a distance. And so in doing this, the reverberations that are necessary to optimize the sound cannot occur. It's long been recorded that there is an effect of this space on sound. The reverberation time is equal to 0.49 times the volume divided by the surface area times the absorption coefficient, and volume is given in cubic feet and surface area in square feet. This equation was pioneered by Sabine in the early 1900s, but composers from much long ago already noticed this effect of space on sound. One of the main examples is Haydn. In Symphony Number 57, he composed the piece to be very light and staccato. This was done for the music room he was in, which was known for having a dry sound. However, in symphonies number 102 to 104, he switched his compositional technique to instead lack any sudden dynamic changes. And in doing this, he allowed for crisp tones throughout the entire piece because it was performed in a space with a very long reverberation time. Our proposal is to instead use an ellipsoid-shaped room. The ellipse has a very interesting reflective property in that when you have a ray coming off of one of the foci, it will reflect off of the ellipse, and all of these rays will eventually converge at the opposite focus. Using simple extrapolation, it is true that this property will also be in an ellipsoid, a 3D shape, rather than two-dimensional. To conduct this simulation, we used COMSOL multiphysics. Our ray was set to 500 hertz, and the ellipsoid had a major axis of 10 and a minor axis of 6. In this image, you are able to see the propagation of the ray from 0.0 to 0.4 seconds. You can notice that as it comes off of the focus, it reflects, and at 0.03 seconds, all the sound converges there. Notice that it does not converge perfectly at a single point because these are sound rays, so they are not sound waves, so they are not perfectly modeled through particles, and also there are imperfections and absorption within the walls, which I will get to on the next slide. In our simulation, we applied general wall impedance and also had air absorption matching that of air in 20 degrees Celsius at 50% humidity. If we look at these graphs, we see that the maximum amount of wall absorption is at 10%, and at our simulation of 500 hertz, this was only at about 5%. This means that in general, the wall absorption can essentially be negligible. The same follows for the air absorption, which is an even lower percentage. Here we can see the sound pressure layer. So this shows the cumulative sound pressure of a cross-section across the XY plane. The sound here is measured in decibels. We can notice that the sound converges on these red spots, which are where the foci lie. There is no residual sound in the areas around the room. This is inaccurate to what would actually happen in such a setting, as the sound waves are reflecting off of the walls and are also present in the room. However, this was below the threshold that we set to maximize our graphics, so they are not visible in the simulation. And the amount of sound present in these areas is low enough that it does not detract from the main takeaway. We recorded impulse responses from 4 different receivers. One of them was located at -100, the other was located at 400, 001, 300. The first two are on the major axis. The third one is located on the Z plane, so we call it the high receiver, and 300 is the focus receiver. If we take a look at the graphs of the impulses that these receivers received, we see that the far receiver, which is the first graph here, only reaches the maximum of about 1.1 pascals of pressure, and the high receiver, which is the fourth graph here, reaches just below 0.3 pascals of pressure. The focus receiver received quite a bit more at 3 pascals. It should be noted that the close one received a lot more pressure by quite a bit at 7 pascals. However, this was due to the fact that it was extremely close to the sound source, and this would not actually be the most effective due to the fact that it is only receiving linear sound, which if we return to our sound pressure layer, we will see that that fact is shown because the foci do end up receiving more overall pressure. Discussion. So the convergence of sound at the focus shows the success of our reflective property, but we have many additional variables that still need to be explored. For example, the effect of a material. So wood absorbs lower frequencies, whilst porous materials such as carpeting will absorb higher frequencies. In concert halls, of course, we have the issues of flooring and people and paneling on the walls. However, it must be noted again that our simulation mostly focuses on the merits of an ellipsoid room in recording applications. And here we can see that the addition of a floor will complicate the reflection paths to a significant extent due to the fact that a flat surface on the ground will heed the ability of the rays to appropriately propagate and converge off the focus. However, if we maintain this ellipsoid shape in the roofing, the extent of this property will still be observed to a significant degree. If the sound source is not at the focus, which means if we are not simply recording a solo instrument or a very small ensemble, so in the case of an orchestra, this means that the sound will be less centralized. If we are not able to reliably propagate sound off of one of the foci, the pattern of reflection will be a lot more complicated and it will not converge as tightly around the focus. However, this property still does stand and is still deserving of more exploration. And in conclusion, the ellipsoid room is able to simulate a concert hall experience much better than our traditional recording rooms due to the fact that the sound is allowed to propagate through the hall and reverberate to get its optimized sound. Here are my references, and I will now take questions.
Wonderful. Thank you so much, Marlyn. And very interesting. Little intersection of physics and thinking about music as well. Do we have any questions for Marlyn? Yes, Hannah. Actually, we have two hands up. I think I saw Hannah's first and then Megan.
Hi, Marlyn. Great job presenting. I really loved your presentation. This question might be a bit unrelated, so it's totally okay if you can't answer it. But did you by any chance research how like radio waves can be maximized, especially now in the time where concerts are like all virtual? Is like the quality of sound the same like over radio or like on Spotify, for example?
Unfortunately, we did not get the chance to explore that. We mostly focused on frequencies of sound that are most common in an orchestra or an ensemble, hence the focusing on the 500 hertz. Megan?
So if the shape you described is the optimal shape, what is the shape that is considered conventional?
So in these photos, you can actually see most conventional concert halls follow this shape. It's generally referred to as a fan box shape. And the idea of this is that it allows for quite a bit of reverberation so that sound is able to reach the farthest most seats. However, this does have issues in that sound is not always able to be optimized due to the fact that some pieces simply require different reverberation times that these concert halls cannot provide.
Thank you. Great presentation.
Thank you.
Great. Do we have any other questions for Marlyn? We have time for one more. Paul.
Thank you, Mara. Great presentation. I'm curious if we need to build structures for just like one type of performance. I imagine like opera presentations might be different than a symphony orchestra. Or do you think like it's equivalent that it could just be like this one setting for both types?
I believe that it really depends most on the uh, articulation of the piece rather than the performer. So based off of like, as I mentioned with the Haydn pieces, a short piece would just simply require a much lower reverberation time. But if it's an instrument or a singer delivering that articulation, it does not matter as much.
All right. Thank you so much, Marlyn. And thank you all for the great questions.